Welcome back friends. So in the previous lecture we have been looking at Dirac propagator, how to derive the Dirac propagator, and the derivation is simple because we know the algorithm now. Essentially the algorithm is like write down the equation of motion for free particle with a delta function source, express the delta function in terms of the momentum modes or in the Fourier space. In this side the wave function or the Green's function is also expressed in terms of the momentum modes, and then in terms of this momentum mode you can equate on both sides, putting it back into the equation of motion, and you get the momentum space propagator from that essentially. So we proceed in the same fashion. The Dirac propagator is nothing but the Green's function which satisfies the Dirac equation, and I del slash minus m sf x minus y 1 into 10 del x minus y essentially. Delta function is the what we have as a source, and then like I said you can express sf x minus y in terms of e power I x minus y, and delta function also we can express in terms of the Fourier components. And once you do that, putting it back into the equation of motion, you get a simple relation that it is nothing but this is nothing but S of p in the momentum space is the propagator in the momentum space is nothing but 1 by p slash minus m, or p slash plus m by p square minus m square essentially. Now the position space propagator is this given by this particular fashion. Okay, this is obvious, and then what we looked at is the pole structure, essentially the pole structure of this. The pole structure is that you had to solve this integral. We want to solve it. It has a pole at p square is equal to m square, and this would mean that at p square when the particle is at mass shell on mass shell essentially there is a pole. So that would mean that in the P0 plane, in the real and imaginary plane of the P0, if you do a contour integral, you consider it as a contour integral. So remember there is an e power ikx sitting here, and so this has to be a well defined function solution. You have to ikx or px essentially sitting here, so it has to be a well defined integral. To do that, so you introduce this I epsilon prescription, the I epsilon prescription which I have been promising you for the several lectures, that I will be telling you why I introduce this I epsilon thing. The I epsilon prescription tells you that what you have to do is in the positive for the positive energies, when E is positive, E is greater than 0, you have to close the contour such that it has to go on the upper half plane. So if you close the contour in the upper half plane, this integral will become well behaved, this integral will become well behaved for P0 essentially. You can express it into P bar, P0 and so on. So and in the negative, for a negative energy, for P0 is negative, if you close it in the lower half plane, you take the residue with the lower half plane essentially. The poles are on the real axis, and what what you have to do for the negative energies is to close the contour in the lower half plane with a minus I epsilon essentially on the pole essentially with the minus. When you close it in this particular fashion, then your integral is well behaved, your function is well behaved, the propagator is well behaved function essentially. This is a prescription, the I epsilon prescription. Okay, so this I am assuming that you have to take you have to do contour integration. You all understand that what is contour integration, and how to take residue theorem and how to do contour integration in complex analysis. Here we are taking this integral, we solve it using complex analysis. It is a real integral, but we want to solve it in terms of a complex plane because complex contour integration. Okay. and if somebody has doubts and everything, you can look at there are several resources of solving this thing. So you please look at Peskin and Schroeder. Or any of the quantum field theory for a gifted amateur, or this thing, or the simplest relativistic quantum mechanics books by Bjorken and Ijel. Relativistic quantum mechanics. Now this is prescription once you do it, and then you get a well defined propagator. The propagator is now well defined, it can be used and everything. What we also want to know is whether this propagator satisfies all the general properties of the Green's functions, which we have listed in the previous lecture. Essentially we have listed whether it is sum of all the states and everything, whether it contains both the negative energy and positive energy states and so on. So the answer is true. You can express this thing in terms of positive energy projection operators and negative energy projection operators in this particular fashion, using this UU bar is equal to P slash plus M by 2M and P slash minus M by 2M. So far this is what we have done. Now, so this is a free propagator, this is a completely free propagator, there are no interactions in this particular case. What happens when there are interactions? What is the propagator in the presence of interactions? So the propagator in the presence of interactions, we have to write it in this particular fashion: I del slash minus E A slash minus M SF prime x minus y is equal to delta power 4 x minus y. Now there is nothing new, this is just the Dirac equation, but with interactions, with the current interactions with the A slash. Essentially A slash is nothing but your electromagnetic field. This is exactly in analogy with how you solve for the wave function. Okay, for the wave function, how did we solve with Green's functions methods? Is we have psi of x is equal to psi 0 of x plus E integral SF x minus y A slash of y psi 0 of x d power 4 y, where psi 0 is this wave function, which is a tree level wave function. This psi is the Dirac wave function. So this is in the presence of interactions, this is the free wave function, that means this does not have interactions. This is the propagator and this one. Now in analogy with this, if the propagator also gets interactions, essentially we should write down psi of x is equal to psi 0 of x plus E integral SF prime x minus y A slash y psi 0 of x d power 4 y. Now what I did was that earlier I took this as a tree level propagator, but now I introduce interactions also to this propagator essentially. So I introduced, instead of S of x minus y, I introduced SF prime x minus y essentially. So how do I get SF prime now? How do I get SF prime in terms of SF? I want to see what is SF prime in terms of SF. I now know that L del slash minus EA slash minus M SF prime x minus y is equal to delta power 4 x minus y I del slash minus M SF x minus y is equal to delta power x minus y. This is the interacting propagator. This is the free propagator. So this means I can get the difference. It's exactly like what we are doing earlier for the wave functions. So I del slash minus M times SF prime x minus y minus SF x minus y is equal to EA slash SF x minus y. Okay, this means SF prime x minus y implies is equal to SF free propagator plus E integral. Now I del slash minus M is nothing but SF x minus Z A slash Z SF prime x minus y d power 4 z. What I did was I solved this equation. Now I del slash minus f also can be written in terms of SF. It is nothing but SF. So you are multiplying, if you take it on the right hand side, it just becomes another SF. So there are two SF. SF prime is on this side essentially. SF prime will also, so it is like an integral equation with both sides SF prime f x essentially. So this is so called the Dyson equation. Okay, this is the so called Dyson equation, which is exactly sets the rules why we need from which we get the Feynman rules essentially. Okay. So this is nothing but the Dyson's equation, and now we can try to solve it order by order essentially. You can have a Dyson series, we can have a Dyson series. So SF 0 x minus x prime is equal to SF x minus x prime, that means it is the same, it does not change. SF prime x minus x1, let me call it not prime, x minus 1, SF x minus x prime plus E integral SF x minus x1 A slash times 1 SF x1 minus x prime d power 4 x1. Okay. So you are introducing one interaction, essentially you are introducing one interaction term. Now the second order, meaning order by order your interaction, you are introducing something, this is called the Dyson series. Okay, Dyson series. Plus the E square term will appear now with two integrals SF x minus x1 A slash x1 SF x minus x2 A slash x2 SF x2 minus x1 prime D4 So, you see a second order term. So, if you go higher order in perturbation theory, you end up having this one. So, the fermion propagator, let me represent it in this particular fashion. This is nothing but x and y, SF 0, it has no interaction. The total, if you add the total Dyson series, that means in the full interaction term, write it in this particular fashion, this becomes SF total is equal to SF 0, that means it is tree level, plus an interaction with a blob x1 plus this is nothing but your Feynman rules essentially. So, two blobs with A, E, X, Y, X1, X2. So, this is nothing but your Dyson series essentially, which tells you how you can do the same thing for the wave function also, you can do the same thing for wave function also. So, this is how you do. Okay. So, the interacting propagator is derived as a series in perturbation theory is continuous like that essentially, it depends upon the precision, you truncate it at what level you want. The statement I wanted to make was that you can do the same thing for the wave function actually. So, you can do the same thing for the wave function. Okay. So, the wave function similarly so, the same Dyson series for the wave function. Psi 0 is equal to psi 0, it is nothing. Psi 1 is equal to psi 0. It is the same equation, okay, it is the same equation which we wrote down earlier essentially, e to the power 4 psi 0 of x. Psi 0 of y A slash x1 SF x1 minus y x minus y. Similarly, psi 2 psi 0 plus e double integral. So, instead of SF you have psi 0 sitting here essentially. So, this is the Dyson series for the. So, where you are solving the same equation which we started off for the general Green's functions method essentially, this is what we are solving essentially. So, general Green's functions method, what we try to solve, this is the same thing. I think we introduced the general Green's functions method sometime here. So, this is the same thing, okay. This is the general Green's functions method, we are using the same thing, the same equation and putting it back here essentially. So, what did we learn? We learned that we can start doing order by order perturbation theories essentially. By perturbation theory we can solve it order by order. Now, how do we solve this thing? Now, how do you interpret this blob? How do you interpret this blob here? Now, this blob, if A is also quantized, this blob can be interpreted in terms of a photon being exchanged essentially. Okay, if A is quantized, that means the wave function of the photon of the EM field is quantized. The quantization of the wave function is called second quantization. The quantization of the wave function is called second quantization. We will come to second quantizations in the coming lectures, but instead of using even a quantization quantity, you can, if you treat it as a wave, so that means that the full propagator, full interacting propagator, if you treat it as a wave, is equal to the tree level propagator plus, in perturbation theory, is equal to the wave function of the photon appearing like this plus the wave function of the photon coming twice between x and y. Essentially here, if you want to call it as x and y, x minus x1 around x1, x1 y, x1 x2, so there is y1 y2, okay, in this series essentially. So the wave function goes out and comes out, goes out and comes out, because it should depend upon, it depends on the propagator, right. Essentially there is a propagator fitting in essentially. Now this is a virtual thing. Now this is a virtual photon, and in between the thing is also a virtual particle essentially. The thing is also a virtual particle. Okay, the in between, whenever this photon becomes virtual, the electron line also becomes virtual. So these are all virtual. This is a propagator inside, and the external lines are the, everything is a propagator anyway because there are two blocks. These are the Feynman diagrams corresponding to the corrections to the propagator. So before drawing further corrections, essentially you can try to see how to solve these particular things. Essentially we want to solve how to solve this particular thing, but before doing that we will do some simple process first. Okay, we will do some simple process. At leading order in perturbation theory. Now the series tells you that, before going to the simple process essentially, let us see what the series tells you, that there is the thing which interacts, which modifies the propagator, then there is the external line itself. So this is the wave function of the photon for the electron, which itself is getting modified because this is has a blob here which has wave function relaxation. Okay, so this has a blob here. Okay, so this is nothing, this is the propagator which is getting modified of the electron. The wave function of the electron also gets modified. Now the propagator we have seen, similarly, okay, similarly the propagator of the photon also can get modified. At the tree level, the propagator of the photon is just this. I forgot to write the tree level external line. And then what does the propagator of the photon get modified with? the propagator of the photon gets modified with blobs like this. What are these blobs? These are positron electron pairs going in the loops. These are created for a very small period of time and then absorbed. So, what we have seen is in the Dyson series, Dyson series is a way of calculating order by order perturbation calculations for the propagators of the photon, for the wave function, and it also gives you for the coupling constant the same method essentially. It also gives you for the coupling constant. So, the full coupling constant would be some blob like this. So, this is equivalent to the tree level coupling constant times coupling constant like this times coupling constant like this. So, what we have seen here is that the propagators are getting modified, okay. What meaning at higher order in interaction theory, the propagators are getting modified at higher orders in interaction theory, the wave functions are getting modified, okay. The wave functions are getting modified when you try to solve them explicitly, essentially they are getting modified, and the coupling constant is also getting modified essentially because of these corrections in the interaction picture. The moment you put in interactions when you are trying to solve it order by order, it leads to all this bunch of Feynman diagrams in propagators, wave functions, and in the coupling constant essentially. So, before looking into, so these corrections have to be calculated higher and higher order, okay. This is I am not doing any field theory, I am not doing anything, this is just perturbation theory with just okay with just Green's function methods essentially. So, if you want, in other words, quantum mechanics in the relativistic framework is nothing but using Green's functions methods to calculate things essentially, to calculate things the way Feynman and originally have done it, and not use the full technology of the Green's of the what we learn nowadays in terms of relativistic quantum mechanics is that you use Green's functions methods to solve scattering process. We can go about up to one loop in these particular things essentially, but the interpretation becomes difficult and it is much better to actually go to second. Of course, you do second quantization, but you quantize the part to interpret actually, but it is better to learn it as a quantum field theory essentially. But for tree level process, the technology is the same, whether you call it once you get the Feynman rules, it does not matter whether it is coming from quantum field theory or whether it is coming from relativistic quantum mechanics as we see now essentially using Green's functions methods. The calculations are identical, and once you use the Feynman rules they are all equivalent, and this is precisely what the Dyson series tells you. The Dyson series tells you that calculations order by order using the Feynman rules method is equivalent to using the full Green's functions methods as has been shown essentially. Good. So, with this what we will see is we will come to the higher order corrections and their interpretations, okay. So, the summary is that Dyson series shows that computation using full Green's functions methods and actually there are Schwinger methods and other methods is equivalent to using Feynman rules to calculate processes order by order. This is nothing but, in some sense, this is also quantum field theory, essentially it is also quantum field theory, okay, but without full rigor of the quantum field theory, without the full rigor of the calculations are identical, at the tree level, but the interpretation is still in terms of wave functions etc. without full second quantization or quantization of fields. So, this is the difference, okay. This is the difference between quantum field theory and what we are doing now. And this is, we are setting the tone, but this gives you a nice transition how to move from quantum mechanics to quantum field theory, and it also gives you all the meaning physical interpretations which we need essentially to going forward to understand why things are so in quantum field theory, why things are so in quantum field theory. So, this is an important background to understand quantum field theory, okay, in a relativistic quantum field theory. Okay, good. Now, given this, now we will start with some tree level processes and then try to solve them. I will give you some general rules and everything, and then we will go what happens in higher order corrections essentially. Okay. I will stop now and we will continue with some simple process in QED. I will tell you some simple process in the next lecture, and the further lecture we will start looking at higher order corrections. Okay. Thank you very much.